Okay, so we have seen a two-stage LNA. Now, what I'm going to do is I'm going to design digital attenuators and phase shifters. Okay, so let's do as much design as we can in this. So the basic element in a phase shifter or attenuator is a switch, and the lower the loss you can do, the better it is. A quick question: are people able to see my screen? Because I don't want to be talking to myself only.
Yes, sir, we are able to see.
Okay, let's proceed. Okay. So phase shifters are slightly more difficult than attenuators. And the idea is you want to do a broadband phase shift. Okay. So I have to make these elements. Okay. So I have to make these elements which are binary weighted. So basically I have to do something which is 180 degrees, 90 degrees, 45 degrees, and what else? 22.5 degrees and 11.25 degrees. Okay, so this will be the five bits. So it will go from anywhere from 0 to so it will go from 0 degrees. So it will go from 0 to 300 and 360 minus 11, which is going to be 350, 349, 348.75, right? 348.75. So this binary weighted sum, well, it can go from 0 to 348.75, and then the next step would be back to 0 degrees, because 360 is 0. Okay, so I would not synthesize 0 degrees. Okay, so I have to make these elements. Now let us see the complication. Okay, let's say so the basic topology is going to be, so I'm going to have a switch which will be a single pole double throw switch, right? And let's make a switch here quickly. Okay, so basically this will go like this. So this is a single pole double throw switch. So I have to make this switch such that it has the least insertion loss. Okay, and it has the highest isolation. So this off isolation should be the highest and the on insertion should be the least. So this is the switch I have to do. And then I will add to this these delay elements. So basically I can put in 180 degree. Okay, and I'll just repeat this, and let's just, come on, I don't want to see this. Okay, and in over here, okay, yeah, so this basically would be directly connected. Okay, so if I was to do something like this, okay, there is an issue. I'll tell you what has happened. Yeah. Come on. Oh my God. Insert shape. Okay. So if I was to do this arrangement, there is a problem. I will not be able to do this broadband. Okay, why? I'll tell you the reason. Hang on. Why is it so stupid? Okay, so if I do this arrangement, on one path I have 180 degrees, on other path I have 0. Then if I was to plot, okay, phase, if I was to plot the phase, okay, what will happen is the following. Come on. Okay, so if I was to plot the phase will go through 180 degrees. Something like this. Okay. Okay, so phase change would be like that. Okay, for a given length, this angle would be more than 180 degrees. So this is a negative number, right? So we are talking about delay. Okay, so here, if this is minus 170, okay, here if it is minus 170, here it is going to be minus 190. And somewhere in between for which you have designed, okay, somewhere in between where you have designed, it will be minus 180. Okay, so you have 180 degree phase shift at only one frequency for which you have designed, and then there is a phase shift here. Okay, now this is not desirable. Okay, so what I'll do is I will split up into 90 and minus 90. So this will be minus 90. So now, okay, what I'll do is I will do one of them. Okay, let's say this one is 80, this is 90, and this is going to be 100. Okay, so now if I can do, so don't worry about the direction, okay, the signs. Okay, this will be opposite sign. Okay, then I will do one element which is like this. The other element is doing the same stuff. Okay, which is starting at as like this, and the difference here is going to be, so I will rather represent this as a delay of 80, delay of 90, delay of 100. And then this will be minus 80, sorry, 90, and then this will be minus 90. Okay. Okay, so now this gap from here to there, come on, this gap over here is going to be 180. That's how this is designed. Maybe I haven't placed it properly. So the total gap here is 180. So now between the two paths, everywhere the gap is 180. One side is a low pass side. Other side is a high pass side. Okay, so this would be called a high pass, low pass element. Sorry. Okay, so I want to design these two circuits which will give plus 90 and minus 90. And then when I see the gap between the two, it's always going to remain 180. So the net, if I switch from one path to another path, the total change is 180. Similarly, I will add other blocks here. Okay, so now this is going to be plus 45 and minus 45. Sorry. And so on. So basically then 22.5, 11.25, and then 5.625. So that will give 11.25. So I need to do these blocks. Okay, so you understood that what is going on here. Okay, so I want to design a phase shifter, which is basically doing this. This, and over here it continues. So let me just put one more line here. So it just continues till I reach the LSB. Okay, so I'm supposed to design this. Now, you can go ahead and look for papers. You can go ahead and do all kind of mathematics, but I don't like maths. I'm like all other people. Most of the other people don't like maths. So I'm like those. So I would have to do my own shortcut where I don't use equations to find out the elements. Okay, so what do I do here? Okay, so the next thing is I will start designing it. And this technique, I think people don't use that. Rather, they go and write elaborate formulas to design these. And I don't think you need formulas for this. Okay, so what I'll do is I'll go to new schematic. So I will just put all of this in one stuff. I'll call this as LNA, new folder. And previous designs I'll put under LNA. So this whole thing goes under LNA. Now I'm going to make a new folder and I will call this as phase shifter. SHIFTER. Okay, and here I'm going to make a new schematic and I call it ELE 180. So I'm going to do a element 180. Don't worry about this. Okay, so how do I do element 180? I'll go to line, ideal transmission line. Transmission line ideal. And what I want a 50 ohm line, which is 90 degrees, because I want to do plus and minus 90, right? And this is at 27.9 mid-band frequency, 27.9 gigahertz. Okay, and that's over here. So my question now is, how do I transform this into a circuit, right? Okay, just one second. Okay, so what I'll do is I'll go to S parameter simulation. I'll put two terminations, 1, 2, and I will do a S parameter simulation of this. Correct? And what I'll do is I will try to find, so if I do a S parameter simulation on this, and my frequency is a single point frequency of 27.9 gigahertz. So that's the single frequency of 27.9 gigahertz. Correct? Up to here, there is no problem. Then I am going to get Y parameters and Z parameters, not group delay, Z parameters. Okay. And I'm going to simulate this. Okay. Once the simulation is done, I have got Y and Z parameters. Now I will write equation. Okay. So what equation I will do is I will fit a pi equivalent. Okay. So what would be a pi equivalent? So there will be like, let's say if it's a low pass element, it will be, let's say, a pi, and high pass element I'm going to put as t. Okay, so let's start with the low pass pi element. So CSH1, well, it will be symmetric, so it's only CSH. CSH is going to be imaginary of, okay, minus of y 1 comma 2 divided by, okay, y 1 comma 2. So this is, sorry, CSH, right? So y11 plus y12. Okay, sorry, divided by 2 pi frequency, 2 into pi into frequency. Done. So this is my shunt element. So let's me calculate this. So this is going to be my shunt element. Done. So this is around what? 11.4 picofarad, right? So this is 11.4. No, I'll just change this equation to engineering so that it's easy. Okay, 140 femtofarad or 0.1, so 114 femtofarads. That's all you have to remember. So there are two capacitors which are shunt, which are this. What about the series element? Series element is going to be L series, is going to be imaginary of 1 divided by minus y 1 comma 2 divided by 2 pi frequency, 2 into pi into frequency. Done. So that is my going to be LS equation LS. Done. So this is one part of the circuit. Okay. What about the other one? The other one is going to be C series. So this is a T equivalent. Okay. So this will be imaginary of Z11. Okay. Minus Z12 divided by 2 pi frequency. So it will be 1 divided by. So let me just confirm this. I think it should be 1 divided by Z11 minus Z12 divided by 2 pi frequency. Okay, so let me just make sure that I'm going right. Element 180. Just give me a second. Come on, this is so stupid. Yeah, it makes sense. Okay, I don't want to do a mistake here and then later come back. Okay, so what this will be, come on, my mouse is not working. Okay, 1 divided by imaginary of this divided by 2 pi frequency, 2 into pi into frequency, correct? So this will be CS. Okay, and then LSS will be Z12 minus LSH. LSH will be equal to imaginary of Z12. Okay, minus imaginary of minus Z12 divided by 2 pi frequency. So this is my T equivalent, that's my pi equivalent. LCS and LSH. Done. They are the same numbers. Of course, they would be same numbers for 90 degrees. So don't worry about other frequencies, other delays. Okay, so I have these values. So I'm going to put a low pass element, which is a pi element here, and a high pass element, which is a T element here, right? So a low pass and a high pass element. Okay, so let's do it this way. Let's go here. Let's do a high pass, low pass element. Okay, so I would pick a capacitance. Okay, that capacitance is going to be 114. So 114 means this is 12 and this is 12. So 148 is too high. 10 and 10. Let's see, 10 and 10. So 104. What do I need? I need 114. 114, right? Okay, let's go back here. Okay, let's look at 11, 11. 11, 11. Okay, so 10.6, 10.6. 10.6. 116. So not 6, 4, let's say. Or let's say 5 and 5. That will be somewhere in between. Okay, so 114.45. So one element is this. Other element is over here. And then there is an inductor, which is 285 pico. 285.2 pico. So I'll put an inductor here. Okay, so number of turns is 1.5. Okay, this is around 23. So 23 is more, 22.5. 22.5. This is 296. What do I need? I need 285.2. So let's see what this is. 289. How much is this? 288. 283. 285 something. Correct. So this is my shunt element. Okay. And I will bring a ground plane out. So basically I will connect a ground here for now. Okay. And of course you have to take care of ground inductance of the ground. But what will happen is that the ground inductance is common throughout. So really I will put a pin here and forget about the ground inductance. So I mentioned to you that the ground comes with the inductance because of the bond wire. So when I put a pin in here, it won't really matter. Okay, so this inductance, because everything will be referenced to this ground, which is an inductive ground. So I don't have to compensate over here. Okay, so let's look at two more terminals here. Sources, frequency domain. Sorry, S parameter simulation. And this is terminal 3 and terminal 4. So this is going to give you a 90 degrees delay, plus 90. And let's look at the pi equivalent, which would be this as the series element like this, and this as the shunt element like that. So this is going to be your, and then you have ground, ground, of course, and then you have got two more terminals, 5 and 6. Okay, so now I will simulate this again. What? Okay, of course you have to put the include file. Sorry, where is the include file? Include file. Yeah, and then hit simulate. Done. So now let's see how does it compare. Okay, let's look at 4-3 phase. Phase 4-3. 4-3 phase. Okay, so it looks like 90 degrees, right? Now let's look at phase 6-5. Phase. This looks like minus 90 degrees, right? That's what we designed for. This one is plus 90, and this one is minus 90. Correct? Makes sense? So now the difference is going to be 180. So it's as simple as that. Design is very simple. Okay, unless you think the scientific way, the scientist way of doing things, and you will go and read thousands of papers and try to find out formulae for high pass element design and low pass element design. Why? You are an engineer, right? So engineer knows how to get the job done. So I got my job done by just putting an ideal line and then just using T pi equivalent, and I have my design elements. Why do I need to write an elaborate formula for computing C and L? Okay, so that's the difference between a scientist and engineer. A scientist will do a lot kind of research and write formulae for L and C. He will do elaborate, what you call elaborate derivation. Like for example, you go to NUS, and NUS there is a PhD by this guy. What's his name? On 2017 it was awarded for this same phase shifter kind of stuff, right? What's his name? I forgot his name. Yeah, so you will find, right? So 2017 his PhD is all on phase shifters. So he has derived an elaborate equation for this, an elaborate equation for these elements and that elements. Well, I know that I'm an engineer, I'm not a scientist, I'm not doing PhD, I'm doing design, right? So I will just write the formulas from my ideal line equivalent, just a T pi equivalent, and I'm done, right? So let's see it across. Let us see it across frequency. So I'm going to go from 27.5 to 28.5, 28.35. This is my design band. Okay, and I will go 10 megahertz. Okay, and I will say done. So once I have done, I know that this is the story, and I will just do a subtraction. So I will take this expression, Control C. I will go to this expression and say minus Control V. Done. And this one I will throw off. So this one I'll throw off. So you have 180 degrees broadband. You see? So it is 180 degrees broadband. So it's like an error of 0.01 or 2, or how does it matter? 0.01 or 0.02. How does it matter? Okay, so this error across the band, you have no issue. Okay, it is a flat 180 degree. Versus if you were to do something like 180 degree element delay on one side, then you will have this slanting like that. Right now, what you have done is you have a broadband 180 degrees delay on all the frequencies. Okay, so now what about the other elements? Well, nothing. It's just that I have to repeat these equations with 45, right? So what I'll do is I will just make a copy of this file, save as, and I will call this as 90. And once I'm done with 90, I'm going to just change this line to 45, and say, okay, I'm done. And I have to just change this element. So I'm going to just repeat this simulation. And I don't want to write the formulas again. I will just copy these guys, Control C, Control V, done. And of course, I have to have these elements. So CSH is now 47 and it is 202.3. Okay, now these elements are not going to be same, right? So now you have 284 and 413. Okay, so 284 and 413.9. Okay, 284 and 413.9. Okay, so of course I'm going to put this in here, and I will go here. So I have to change this value. This value comes out to be this is 180. So I'm not going to touch this one. This is 90. Yeah, so the new values are 284. So let's do this as 284. So for that, I will be somewhere around 18, and I will be 18 here. So that is 331. So 16.5 and 16.5. 16.5. 280. How much do I need? 284. So 16.8. Okay, 16.7. Yeah, 16.6, 16.7, 16.6. It's going to be slightly square. The 16.7. Why you draw pi network? Can we directly simulate figure? Just 1 second. I'll answer this question. Okay, what is your question? Why you draw a pi network? Can we directly simulate first figure? What do you mean by that? Can you just rephrase your question? Because I don't understand what your question is. What's your question here?
Hello.
Yes, I'm listening.
Yeah. Because the transmission line is a phase shifter, which shift the phase of the frequency signal directly.
Yes.
So why we draw this two
Okay, very simple.
circuit
I'll
below the
answer.
first
Yeah,
one?
I
Like,
got your
yeah,
question. I got your question. Okay,
yeah.
so let me put on mute and then I'll answer the question. Okay, if you were to just use a transmission line, so what is a transmission line? Transmission line is a low pass network, which means that you have come back to a scenario where you don't have a high pass element. You just have a delay of 180. So what will you put on the other line? Right? Because transmission line basically is a low pass network. Now, if you were to do like you would say, I want a difference of 180. Okay, so how do you get a difference of 180? If you have 180 on a line, then you have a 0 on the other side. How do you generate a phase advance of 90? So you have to go to one network being high pass, the other network has to be low pass. If you just use transmission line, then both are low pass. So if both are low pass, and secondly is what would be the difference, right? So basically the bandwidth you will not achieve if you just use transmission lines. So if you see this bandwidth, you will not achieve if you just use transmission line, because both are going to be low pass elements. And then the difference you are going to guarantee as 180. So this additional 180 would anyways will not be broadband, right? So you need a low pass, high pass element. That is why one of them is a low pass element, other is a high. So that's the equivalent. Okay, so you cannot just accomplish this with a transmission line. Okay, because transmission line is just a low pass element. So have I made myself clear? Like, can you? Okay. So you understood why I cannot just use transmission line and then a phase difference of 180, because how would you get the bandwidth then? So that's the whole idea. Okay, so one side has to be high pass, other side has to be low pass, so that the difference remains constant. Okay, if you just take two low pass elements, they will be unequal side, and then the phase delay will not remain constant. Basically, then you will not get the bandwidth out of this. So you need a high pass and a low pass equivalent. So let's go back to where we were. Okay, 200 and so I need to create 284. Okay, so where were we? Okay, so this is 285. Okay, I want 284. This is 283 or 284. So it's okay. I'm not going to go to a final resolution. And then I'm going to replace this with this capacitor. And this one, inductor, if you go to this, the inductor is 413.9 pico. Okay, so basically I would make this as 35. So 35 is more. So 34, 413. Okay, so probably 31 is good enough. Not even 31, 30. Okay, 29 point something, 29.5. Okay, so you have 413. Okay, 6, 14. Okay, roughly this one. Okay, so this is done. What about this one? This one is going to be 47.18 and 202.3. Now the problem is 202.3. So if I go to the lowest radius, okay, then also it is not 202. Now, there are two ways of doing this. If you are going to take care of your DRC LVS, then you can do a custom inductor here. If you don't want to do custom inductor, I am going to put two inductors in parallel. Of course, it's going to take more space, but then if you want, you should do a custom inductor for yourself, which will be just a line. Then LVS you have to do manually, because the inductor in layout is just a trace of line. So it will not be able to do LVS unless you put a dummy layer. So if the process allows you to put a dummy layer and declare an inductance, then it will be able to do LVS. Otherwise, you have to do your LVS by manually. Okay, and in that case, you might do errors. Okay, so what I'm going to do is, if the requirement is 200 and 202, I will do 404, and I'll put two of them. Okay, so it will be 229.6, right? As we compute it, 404 we want, right? So 29.2, that is 405, 29.1, that is 403. Okay, 2, apply. Okay, so this is one inductor, and I'm going to take another inductor, put it in parallel. Now, this layout is going to be complicated. It's going to take more space. What I would do is I would do a custom inductor, which is going to be just a stretch of line, right? And I would just say simulate. Oh, did I change the shunt capacitors? No, the shunt capacitors are going to be, okay, the shunt capacitors are going to be 47.18. Okay, so this one, let's do what value should I put here? 6 and 6, 38, 47.18, 7 and 7. It will be too much. 6 and 6.5 and 6.5, 5 and 6.6, 47.18, 6.6, 46, 6.7, 46, 6.7. Okay, roughly that. Done. So I will just paste this over here, and I'll just simulate this. Done. Simulate. Okay, so you have 89 degrees over here, 88.9, 89 degrees. It's not 90 degrees. It's because this capacitance is slightly different, right? Okay. Okay. Let me try the other side. 6.8, 6.8. I will go back to 6.6 later on. Yeah, understand. Okay. 6.8, 6.8. So this is because our inductor is not accurate. 89.72. Well, I can adjust the inductor also. Okay, so I wanted a more delay on this, right? 3 and 3. And simulate. It's still, come on. I don't like these minor adjustments. 4 and 4. Okay. Again, 0.9 E. Maybe I'll work with this one. Why would I have inaccuracy only on the one side? It's not doing much. Come on. 5. Okay, there we are roughly. Okay, so now we are going 90. Okay, 90 degrees. So we are done with other element. So I have got 2 of this. I have done 180, 90. Now, if I keep on doing this, I would run out of the lower and lower values here. That's a problem, right? So now here I would have a band pass element. So it will be high pass, band pass rather than high pass, low pass. So all I have to do is I have to put one capacitor here and that's it. Okay, so let's just do a 45 degrees line, right? So this is done. Okay, let me make 2 components out of this. Okay, so what I'll do is for this one, I will just say copy cell and then I will add a C to this and say put it in this folder. And this is a component. And this component, I am going to throw out this guy. I'm going to throw out this and this and this, 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 and this. And I have HP1, HP2, HP1, HP2, LP1, and LP2, and ground. This is the ground. Done. Okay, so this is my low pass, high pass element. I'll make a symbol for this. Okay, so new symbol and create a symbol and say okay. So high pass, low pass. And just make it smaller. Rotate this around. Done. I'm going to make this only one time. Next time, I'm just going to copy it. Okay, so this is done. Now, what is next? I'll have to make a symbol for this one, right? So what I'll do is I'll just copy this, copy cell to 90C. 90C. Okay, done. And in this 90C, I have to replace these guys. Okay, these guys I have to replace. Okay, so to replace it, I will just go here to 90 and pick up those from there. So I want this without the ground, and I want this without the ground. Control C and Control V, and that's it. Just do a ground connection here and this door. So this is a low pass, high pass, low pass element for 90. So we are done with 2 components. Now let's do 45. So I'm going to take this one, new, and I'm going to say copy cell, copy cell, and I'll do an element 45. Okay, so element 45, I am going to go here and change this. This will become 22.5. Okay, so now I have to just simulate this. Okay, I don't have to write a single formula. I will just copy it from somewhere else, which is over here. Just want to copy these. Control C, Control V. Okay, so don't worry about this because we haven't compensated. So now the top guy is okay. All we need is a 590 and 766. So there is no problem here. The problem is 22.69 and 109.2. Okay, so that's the problem. So let's see what fix do I do here. Okay. So I'm doing a 45 degrees now, right? Okay. 109.2, right? And 22.69. Capacitors are still possible. What about this one? This one is still possible. So what I'll do is I'm going to put a custom inductor here. Sorry. Okay, so I'm going to put a custom inductor. So I'm not yet going to do a band pass, okay, for this element. Yeah, this one I can just delete it. Okay, so I need 590.6, so 0.5 picofarad and 0.766 nanohenry. Okay, so over here, I want 0.5. So let's look at 20 here and 20 there. Okay, so it doesn't work. 23 and 23. So what I want is 590, 24 and 24. Sorry, 24 and 24. So 585, 24.2. And let's say 24.2. Okay, so what do I need? 590. Okay, 24.1. Roughly 590. Okay, so this one is 590 and this one needs to be 590. So I'll just copy this over here. That's 590. And the inductance I want is 0.766 or 766.6. Okay, so I can go here, 766.6, 26, 25, 766.6, done. So this part is done. What about this one? I'm going to put a custom inductor here because this inductor is still realizable. Okay, so all I want is an inductance of capacitance of 22.69. So I want a capacitance of 22.69. What? I did a mistake. I edited the 90-degree element. Okay, so just 1 second. Control C. Control C. Okay, let's put it back to where it was. So this is a 90-degree element. I'm not going to change that. This is the one which I have to change. Right. Done. So this is done. And this I'm going to add it now. Okay, so this has to be 22.69. So let's put here 4.5 and 4.5. Okay, 22.69. So 4.6 and 4.6. 23. Okay, 22.69 roughly. And I'm going to throw this guy off. Fine. And then what do I need? I need an inductor of 109.2 pico. So I'll just use right now a lumped one, but later I will simulate a trace of line, which will give the same inductance. Okay, so let's say 109.2. 109.2. Maybe I can still create 109.2. Just one second. Go here, go to GPTK and pick up an inductor and do this as 1.5, and radius is fine. I make this as 10. And no, it doesn't look like I can do this. Maybe if it's a 20, it will be a big inductor. It will still not be 109. 109 will be 218. Okay, 218. 218. So 15. 218. 12. Okay, so roughly here. 218. 11.6. Sorry. 218 I want, no? Inductive width 12.3. Yeah, roughly here. Okay, I'll put 2 of them. Usually you should just replace it with a custom inductor, which will be just a trace of line. But no problems. I'm going to use this for 45 degrees. Done. So this is 44.37. Okay, so I can increase the delay here, right? So I can lower these inductance. Well, I have to increase this inductance value. Okay. Now somebody would say that we are looking at half the picture. So nobody told me that. Okay, we are looking still at half the picture. What's the other half of the picture? What about the loss? Are the losses the same? If the losses are not the same, then with the stepping, your attenuations are going to change, right? So that's the issue. And what about S11, S22? What about 50 ohm match and all that? We were not looking at it. So let's, before even I go ahead, I am going to go back to my 180. Okay, so I'll go to 180. Okay, and I will simulate this. And I will look at S11 and S22. S11 and not S11, because S11 is ideal, this thing, S33 and 44. This is going to be your high pass element, S33 and S44. Where is it? It is at the center only. What about this one? This is just underneath that. So basically 50 ohm match was not a problem. What about the insertion loss? Okay, so I want to look at in both paths whether I have same insertion loss. S33, S44, S55 and S66 also I will see. S55, this is going to be the low pass element. S55 and S66. So I'm looking at the 50 ohm match. So everything is at the center. So really it is not a problem of matching here. And what about S43 dB? So S43 dB, this is going to be loss in one path. Okay, it's very less. And what about the loss in the other path, which is going to be S65 dB. Okay, so the loss in the other path is high, is hardly any difference. So we are okay with this, not an issue. Same thing I want to repeat. So basically I would have copied that. Okay, so just one second. Here I would just copy these, Control C, and let's look at what happened in the 90-degree one, Control V. Okay, so we are still at the center, but here there are some loss differences, but they are in like 0.1 milli dB. So really it doesn't matter. So I'm just going to leave it like that. Now somebody would ask me, why such low numbers? Because this PDK is made for you, to make it simple for you. When you put a realistic stuff, you will start seeing like 0.2, 0.3 dB loss here, right? Okay, so this PDK is made for freshers. Okay, for the experienced people, they will be given more difficult stuff. Okay, so right now we take the liberty of doing easy stuff. Okay, so where were we? We were modifying this 41, right? So we did this and we did the simulation. And this was 44.37. Control V. What about the S parameters? Okay, so it's fine. It's not going to kill you. Okay, so now let me just increase this slightly. I want to hit 45. So let's increase this guy. Oh, reduce this guy. 24.7. Done. 44.5. Okay, I need to adjust something on. So this basically is increasing the lead, the phase lead. Okay, this is increasing the phase lead. 44.5. It's not doing anything. Okay, so I'm going to delay this. Okay, so here I'll put 20.4 and 20.4. 20.4. Done. And hit simulate. 44.8. Still, I want something more. 1 or 2 iterations. Don't worry about it. This is going to be 8. And this is going to be 8. Done. 45 degrees. Okay. So I have an error of 0.1 degree. That's okay. It's not going to kill me. Okay. And then the two paths have a difference in, sir, if we could have mismatch or significant insertion loss, then what should be done then? Now, again, I would have ask you to rephrase your question. Okay, please tell your question. Please ask your.
So like to achieve this phase shift, if by realizing this pi and t network, if we would have some return loss that is not appropriate, then
Yeah.
what should be the adjustment that we need to do?
See, if you are writing an equation, okay, if you are writing an equation like the one which I have written, these equation, you are highly unlikely to have that. Now, if you are basically writing the equations based on, some paper, okay, who have given you high pass, low pass delays, and they have designed high pass, low pass, right? So what is going to happen is they design for a certain mismatch. Okay, so those formulas have inaccuracy. This one won't have. And as long as VSWR is better than -15 or -15 dB return loss, you are okay. If you become very bad, like -3 or -4 dB, then your design was wrong. So my explanation is this: if you have used correct formulas, you will not see the mismatch. Because what did I do? I did an equivalent for a 50 ohm system, right? So all these equivalents are written for a 50 ohm system, right? So how can you have a mismatch? You will have mismatch because you use those formulas which somebody has derived. Okay, and in their derivation, they are tolerating over a bandwidth, they are tolerating certain VSWR. Well, they were wrong their formulas were wrong. Right? If you design for 50 ohm, which I have done, so that's another drawback. Okay, over there in their thesis, okay, his guy's name is Tang. Okay, NUS 2017. He has done his PhD. I don't know under whom, but his name is Tang. And if you want to look for his thesis, look for Tang XY NUS. You will find all the formulas. But his problem is going to be the same problem, that across bandwidth, he is going to have certain mismatch. That's his problem with the formulas. I am here doing a 50 ohm system. I won't have a problem because I'm designing for 50 ohm system. Okay, so the problem is not with the design here. The problem is going to be with the formulas which you use. I'm trying to use the most accurate I can. That's what an engineer is doing, right? Okay, so I don't know about the research. If you want to read his thesis, you will find that across bandwidth, he will say there will be certain viswar in this formula. Okay, that depends on the derivation of the formula. So basically his PhD is fine, but then his formulas are not fine. For me, it is, I'm designing for 50 ohm system. It will always look at the center. Okay, now it will not look like at the center when you use a high pass and a band pass. Okay, so the next alteration which I do, I will have to tolerate certain mismatch. But as long as that mismatch is better than -10, -15, I'm okay. So in the next few elements, you are going to see mismatch, because that's not going to be low pass. That's not going to be high pass, low pass. That's going to be high pass, band pass. So as soon as I put a band pass, I am going to see a certain mismatch. Okay, because that's an approximation. That's not the exact formula. Okay, so then I will start seeing the mismatch. I can modify the mismatch. Okay, I can modify the mismatch to be very low. But if your designs are correct, you will not see the mismatch in a phase shifter. Okay, it will be -15 or -10, something like that. Okay, so let's go to the more difficult elements. Let's say 22.5. Okay, so I have to do now. So let me make a component after this. So what I'll do is I will take this one and copy cell. And what I have done is a 45 degrees element. Okay, so I have to do 2 more elements now. Okay, so 45-degree element. Okay, and I will modify this. I will throw off this guy, and I will copy it from the schematic which I just designed. Come on. Okay, I can get rid of these guys. Control C and Control V. Okay, so I'm done with 45 degrees. Now I'm going to do 22.5. Okay. What I would suggest is we take a break, because we are already hitting 240. So we'll meet at 310. Okay, so let me just stop here. Okay, let's take a break of 30 minutes, and you see what I have done. That's the most simplified way of designing these phase shifters. That's the most simplified way. Okay, you will not find it in books. Okay, so I'm going to save this, and I'm going to put this recording to a pause recording. Okay, so now we are going to construct a 22.5 and 11.25. So these are the most, well, these may be the most problematic things. Okay, so now let's see what else is open. Only this is open. Fine. So I have just changed this to 11.25. I'm going to simulate this, and I'm going to copy the data display of 45 degrees. I'm going to copy this data display. Control C, Control V. Okay, so now what I'm expecting is 11.24, right? 5. Okay, so I need 1.192 picofarad and 1.5. This is still doable. Okay, this is still doable. So I'm going to do that. So let's go back here. So I have this as 590. So what I need is 1.2 roughly. So I need 2 capacitors. That's it. I just need 2 capacitors. So I'm just going to repeat them. 1 and one over here, and the story here. So this guy is done. Then I want 1.5 nanohenry. 1.5 nanohenry. Okay, this is also at this frequency doable. Okay, so I would just do something like 34, not yet, 38, 42, 1.5 nanohenry, right? 42. So this inductor has become bigger. Okay, 1.5 nanohenry. 42, but still very small. Actually, if you see the layout, it's going to be very small. 43, 44, 44, and 44.5. Yeah, done. So we are done with this element. Now let's look at the other element where the major problem is going to come, right? Okay, so what I'm going to do is I need capacitors which are 11.24. This must still be doable, and this one is also doable, but you know, there's a problem here, right? So let's do this way. Let's go here to the least possible value, which is going to be 4 and 4. Below this, it's going to give you a DRC error. Okay, so let's say 4.4 or 4.2 or something like that, slightly larger than the, yeah, 4.1. Okay, let's make it 4.1 and 4.1. Okay, so we are done with the capacitors. Okay, so whatever we have computed over here, okay, we just don't worry about it. Okay, just try to pick up the least capacitance you can pick up. Okay, now the question comes is, okay, this is done. Now the question comes is, what about the inductor? I'm going to throw out one of them. Okay, and I'm going to pick up some kind of a small inductor value, right? So the smallest possible would be this one, 219. Now I would have to do a custom inductor here because what I'm expecting over here is 55.65. Okay, so what I'm going to do is I'm still going to do here a custom inductor, which will be just a trace. So I'm going to put here a custom inductor. So this is the first time I'm using a custom inductor. All other elements have whatever the library provided me. Okay, so here let's do something like 45 picohenry. Okay, let's put a loss 0.08 or something. It's going to come with a loss. Okay, now I'm going to put here a coupling cap. Okay, so I want a large capacitor here. So large capacitor, mim cap, and I want a large cap. So it's just like a coupling cap, 30 and 30, right? And rotate here. So this is more like a band pass match, right? This is like a band pass. Okay, and let's make a big coupling gap here. Done. Let's see how bad is bad. 22.9, and our match basically is problematic only on the one which we have done. So what do you need over here? We need a little bit of more inductance to go up. And what about the phase? The phase is doing okay. It's just that I need a little bit of inductance to go up. Or and second thing I'm observing is if I take inductance up, there is an issue. If I take inductance up, then this value is going to go up. Okay, so other thing is this capacitor can be increased, but this capacitor cannot be increased beyond this point. So okay, let's put 3 capacitors. This will still allow me to do this. This would be like a very good coupling cap, but I don't think this is going to do much. So it doesn't do much actually. It doesn't do much. 3 capacitors don't do much. Okay, so let's look at S11, S66 and S55. How bad is that? S66, sorry, S66 and S55. Okay, minus 19. So we are okay, you know, as long as it's better than minus 15, we are okay. But the issue is I need to reduce this further. This is, and if I reduce this guy, then the problem is the following, is that this is going to be this is return loss is going to reduce. So this is going to reduce and this will come to 22.5, as I said, but this is going to move away. So that's the problem with this. Okay, so there is another way of doing this. Okay, which is let it be 45. Okay, let this be 43, 43, 43, and 43. Okay, let's simulate this again. 23.8, and this has become worse too. Okay, so 4 and 4, apply 4 and 4. Okay, sorry. Okay, so now we are okay. Not that bad actually. We are okay. It's again minus 20. It's just that we have a 0.05 dB variation over here, but that's okay. So this 22.5 also looks okay. Nothing much here I'm going to lose. Okay. So what else? Okay, so this one I'm going to make another component. So I will just copy this 45, sorry, 45C as 22.5. Copy cell, sorry, copy cell. This 22.5 component, 22_5. Okay, now over here, I will throw this out. And instead, I will put this one in. So I don't want this, I don't want this, I want this, Control C. And here, I'm going to put that, Control V. Okay. Okay. What? Okay, so we are done with 22.5. Now we are going to look at even more difficult problem, which is 11.25. Okay, so I'm going to look at 11.25. So I'm going to go ahead and copy this cell. It's 11.25. Okay. And then this will become 5.625. Okay, let me just pause here for a second. Resume recording. Okay, so I'm just going to run this. And I'm going to copy the data display from another place. This is my data display. How bad is this one? Not this one, this one. 22.508. Okay, 22.58 and 22.46. So basically there is error of 0.08 on this side and minus 0.0 something. You can adjust to the center and then this error will not be that bad. Okay, so that's okay. It's not that bad error. Okay, so I am going to copy this stuff. Control C. And I'm going to paste it into the new Control V. Now, let us see what is the story now. Here, this is too large. I'm really not interested in using this. Okay, so can I do the same thing as over here, which I'm doing with the low pass? Can I do something over here as a high pass stuff, right? So if you don't mind, I will look at my previous implementation. Okay, so if you don't mind, I am going to look at my previous implementation. Close workspace and go to RF practice, large signal system COMSYS class E RF practice. And let's look at my implementation of common elements, phase shifter. Okay, let's look at elements and 11.25. Okay, so that's what I was talking about. Okay, so I am not going to work with that stuff. Okay, which is basically, so I have here swapped. Okay, so this is my high pass element. I don't want to increase these values, so I started with the same value and put an inductor here. Same way as over here, I started with pi and put this over here. So what I'm going to do is I'm just going to copy this because I don't want to struggle with this anymore. Okay, I'm going to copy this one and go to and close this workspace, go back to my workspace and go over here. You are implementing phase shifter elements over here. So a little bit of cheating is allowed. I don't want to struggle with it, but the idea is very simple. Okay. Control V. What happened? Yeah, it did Control V, right? Okay. So this pi element is this element. And this T element is this T element. Okay. Now, so okay, let's simulate this. Okay, so now if you see, now we have now beginning to see this mismatch on both sides. Okay, we are beginning to see mismatch, though we are 11.25 degrees over here, we are minus 15 here, we have a mismatch here, and we have imbalance over here. So that's was what you were referring to. But you can, of course, you can work with this in a sense that if you spend more time, you will be able to figure out a bandpass match which can be improved. So in this case, this series capacitor has to be brought down. So this is basically going to be 3344. So this is going to be your high pass side. This is your low pass side. So this low pass side has to move up, which means that inductor has to be increased. Okay. And in this case, this has to move down, means that the capacitors have to be reduced. So over here, these capacitors have to be reduced. Okay. And this inductor has to be increased. Okay. So of course you can spend some time with this and try to see what is the best you can get in terms of return loss. Okay. What the best you can get in terms of return loss, still maintaining your 25.25. Okay. So hang on. So this has a series, this one, right? So even this is the top thing, right? So but this is a high pass element, right? So we will go the other way. This will improve, but this will degrade. Okay. And how would I manage this? Lesser delay. Lesser delay means inductor has to be dropped. Okay, inductor has to be dropped. So there is a dilemma and mismatch here, right? So you want to generate something which has this phase balance, but then you are stuck with, you have to tolerate that. Okay, so I'm not going to spend a lot of time on this. I am seeing that there is a delay of 11.25, right? And then there is a mismatch over here, which is better than 14 dB. So if it is better than 14 or 15 dB, of course, there's a difference over here. Again, this difference is not much, 0.1 dB. So now I'm going to live with this. I'm not going to go ahead and change this. Okay, so we will leave it up to here. Okay, so I am going to make a component out of this. So I will go here and save this, copy cell, and this make it as 1125 component. Okay, and then I'm going to go to this, sorry, 1125 component and replace it. 1125 component, and I'm going to replace these. Okay, I'm going to copy from here. Okay, these I'm going to copy, which are like this. Control C. And then we are going to do Control V. Come on. Oh, funny EDS. It won't let me put. That's funny. Yeah. Grid. Half the grid size. It's okay. Doesn't matter. Done. So this is our 11.25. Now let's have a small talk on why 5 versus 6 versus 7 or whatever. Okay. Question goes like this. The LSB is 11.25. Do I need to go to a much smaller LSB? Well, this phase array, okay, this 11.25 step, okay, so this phase array, if you want to do much finer steps, okay, much finer steps, let's say 5.625 and even further smaller than that, is this going to result in any accuracy on the whole phase array? And second thing is, how difficult the calibration of that phase array going to be, right? So if you read some papers on this, you will know that people don't find any advantage going lower than this phase step. Okay, so you will find usually a 5-bit is sufficient enough for most of your applications. Okay, if you go finer than this, that accuracy which you achieve will be diminishing return. Okay, so I won't go to 5.625. Okay, not just that it is more difficult to implement, but again, if you see, why would it be difficult to implement? Because now the line is not 180. The line is basically only 5.625. A 5.625 degree line, okay, difference between the two. Really, you can make another bit with some kind of a variation over the band. Okay, so some kind of variation of the band you can tolerate, because you have gone down in the step to 5.625. Now, do I need to implement this as a band pass? If I want, I can. Okay, it's going to be slightly more difficult. It is going to you have to tolerate more mismatch, right? But what you can do is you can just use two lines which have a differential of 5.25, 250 ohm lines, which is a differential of 5.25. And that would be good enough if you want another bit. You do not have to design band pass and other low pass, high pass element. That's what my opinion is. My opinion is, once you have gone down in angle to such a small angle, right, you need not implement this as a high pass, low pass. You can just take two lines which are differing in phase by 5.625, and that's it. That will be your LSP. Now you are going to tolerate some mismatch, okay, on these phases, okay, or what you call the RMS error. Okay, so anyways, that error is, if it is less than the half the LSP, okay, so that will be tolerable, right? So you should be able to do another bit using two transmission lines differing in phase by 5.625, and you will be done with it. So according to me, for another small element, you need not put a high pass, low pass, or a band pass element. You can just use the length of the line, because the angle has gone so low, okay, that the error you accumulate across band is not going to hurt you. Okay, so even if you want one more element, okay, you can stop at 11.25 using circuit elements, and then you can just use a transmission line to get the other bits. But according to me, if you go 5.625 and below, this will not result in any system accuracy on a phased array. So 5-bit is good enough for most of the applications. So I don't think there will be application where you will need to go 7-bit or 6-bit or 7-bit or 8-bit. Okay, and even if you have to go, don't implement them as a high pass, low pass, band pass element. Rather, just take two lines, okay, and then let them differ by 5.625, or let's say again 2 point, something, whatever is the half of it. Okay, so don't use beyond this. Don't use these equivalent elements. Just use the length of the lines differing by an angle, and you will accumulate certain phase error across the bandwidth. That would be tolerable. Okay, so according to me, as soon as you go in very small angles, you do not have to design these. You can just do a line difference, and that should be good enough. You will not accumulate a lot of error across band. So according to me, this is done. What else I need is a switch. So I'm going to make a Spdt switch quickly, because we want to finish at 4 o'clock. Okay. So what a switch would look like. Okay. Just give me a small break. I'm going to use this element. Okay. Just 1 second. Okay. So we are going to need a series pass element. Okay. So I need some big transistor as a series pass element. So this is 60 micron. Okay. Now, a little note about these SPDT switches. These are like absorptive switches. So even if the path is off, you are still going to see a 50 ohm, right? So let's mirror it. Okay. So come on. Okay. So let's construct two paths. This is a series element. Correct. And then you need some kind of a, so you are going to control the serial element with some kind of a control signal. So here I'm going to go and put a big resistor, high res poly. Okay, high res poly. Okay. And let's say this is 2K or something. Okay, now if there is no current, width doesn't matter. So if there is no current, then width doesn't matter. Okay, so this is a 2K element. And then I'm going to use a capacitor, which is a bypass capacitor. So let's make this as 28. Big capacitor. Any big capacitor will do. 28 and 28. And there it is. So I have one element, which is a series pass element. Other element is going to be a shunt element. So I need a, not a RF capacitor. I need a NMOS. Okay, so I am going to have 5, 4, 4. Okay, and this is your series pass element. And again, you need something like this. So sorry, I'm going to copy this, rotate this, and place it over here. Done. And the next thing is I can just short this guy, and this guy short here, and then I need almost a 30 ohm or 35 ohm resistor plus the channel resistance. The total resistance should look like 50. Okay, so I am going to use low res poly, and this I'm going to make a 35 ohm resistor, right? And this is a ground. So this is all ground. Done. And then I need this, okay, and a capacitor, okay, another coupling capacitor. So I can copy this capacitor. This would be a coupling capacitor over here. And this capacitance value I can take still way up. So let's say that this is going to be 30, 30, 30, 30. Okay, now I'm going to tell you something. Okay, now I can connect this like this, right? So I can always connect this like, come on. Okay, I can connect it like this. Now, one thing can happen. Okay, so we should know that in a SPDT switch, so this is one path. The other path is going to be a parallel path, which is over here. Okay, so how it works is, okay, fine. So how it works is, I'm going to have a coupling cap over here also. So I have port 1 here, port 2 here, and then there are control signals, right? So let's say this control signal is S. So I'm going to turn them on in tandem. So basically, if I name this as S, so this is S, and then this is S. And this one is SB, S bar, and this one is S bar. Okay. So what I have done is when I have S as high and SB as low. Okay, so when S is high, then this path is through, and SB is low means this is off. So between input and output, I'm just seeing this pass transistor. What about the off path? In off path, SB is low, so this is off and this one is on. So now when this one is on, then this equivalent resistance of 50. So whatever is the device here, it sees a 50 ohm termination here, and this acts like an open circuit. Okay, so basically, if that's how it works, one pass element here is on and the shunt element is off. So this is a through path. In this case, the pass element is off, but the shunt element is on. That means that this terminal is terminated into 50 ohm, right? So this is very simple. Now, what happens is what is the power capability of a switch or the insertion loss? The insertion loss basically depends on how large this pass transistors are. If you make these pass transistors large, right? So then between this port and this port, when this is on, this port and this port, the insertion loss is going to go down if you make this transistor large, right? And again, if you want to maintain the symmetry, this will also go large. So, but then if this goes large and it is off, in reality, it is not off. Why? Because the output capacitance is large now because you chose a large pass element. So when the output capacitance is large, then even if this device is off, there's a coupling between this and that, between 1 and 3. So if there is a coupling between 1 and 3, so your off isolation is bad. So your on isolation improves because you made the pass element to be big. But your off isolation has degraded. It is supposed to be high, but it is low because now the output capacitance is large. Okay, so the output capacitance is large. This will cause this to happen. Now, what about the current capability? So we have talked about on insertion, off isolation. What is the power capability of the switch? Okay, so now this through path is fine, and this shunt element is off. Okay, shunt element is off. Now, if you make this element to be very small, then the leakage from the RF path to ground through this element is going to become less. So what it means is first of all, your insertion will improve. If you make this small, your insertion will improve. So this is supposed to be large and this is supposed to be small. So your insertion loss will improve. Okay, next thing is, let's look at the off path. Okay, so if this is through, then if this one is a large transistor, there's a big capacitor here, and this one is on. So basically, your switch has two paths now. One is going what is desired between 1 and 2. But what has happened is, as you start hitting it with power, more and more power is going to this shunt element to ground. And the only way to protect that was if this transistor was small. So for power capability, this transistor is supposed to be small, right? And you do not want to have a leakage path. So now what will people do? People will, instead of using a single transistor as a pass element, you can put two transistors as pass element. So when you do that, when they're off, the two capacitors are going to half because there are two elements in series now. So these two capacitors are going to be in series. So the net capacitance will be small. So the power capability of the switch is going to go up. So you understand. But then again, the insertion loss will degrade because now you have to pass through two transistors. Okay, so the switch design basically we have to worry about insertion loss between the on path and isolation between the off path and the power capability of the switch. And all these are contradicting requirements. So the real design is, you can always put another series element over here, another series element. Now, people will try more crazy stuff. they will take this capacitance and anti-resonant with another inductor. So they will put an inductor across this pass element. Shouldn't the substrate connection be connected to the most negative? Well, this is a twin tub process. Okay, I'm assuming this is a twin tub process. This basically is Silterra, right? So if this is Silterra, then it is a triple tub process. So if this is a triple tub process, then all the devices are sitting in their well. So if they are sitting in their well, you can always short the body with the source. Okay, so here I have done a mistake. So you are correct. So you are saying that it should go to the source. So there was a mistake in connecting this. Okay, this should be connected over here, and this should be connected over here. Okay, thanks a lot. Thanks a lot. So I understood what you mean by that. Okay, it has to be to the source. Yes, the body connection has to be to the source. So that's fine. And the source has to be at the known potential. So that's why the source is always on the input side. Okay, so thanks, Nazif. So I did a mistake there. Anyways, so now what people will do is people will put an inductor across these devices and try to anti-resonate out this. Now that makes the switch as a narrow band switch. Okay, another thing is, to improve insertion loss, I can insert certain inductance here. Okay, a small inductance which will be a trace of line only. So let's say if I put 20 picohenry over here. So go to lump components, and I'm going to put here a 20 picohenry. Okay, something like 20 picohenry. Okay, fine. And the same 20 picohenry over here. So this is going to further reduce the insertion loss. Why? Because if you design this properly, then you can basically have a series resonance here. So the inductance, so the basically this would be a short, and that would result in a lower insertion loss. Okay, so let's just try this. Let's add 2 pins to it. Okay, so let's add 2 pins to it. Okay, this is P1, this is P2, and this is P3. And then I need S and S bar. So I need 2 more pins. Okay, one S bar, and 1 ground. Okay, so this I will call as S, and this I will call as SB. Okay, and then I will have 1 pin as a ground. Okay, so now I will just name them, not connect them. This is a ground, right? So this is a ground. So this I can connect here, is it? Come on. Will it connect here? Doesn't matter. And this I'll connect to ground. So ground is taken care of. I can get rid of this guy. Come on. Okay, let it be. It's not going to cry. Okay, this is S, and this is SB. So my switch is done. I'll make a symbol for this. Okay, I will make a symbol for this. Sorry. So a switch is done. I'll make a symbol for this. Create a symbol. And I am going to make something where I can fit it easily. So I am going to do this. No. 1, 2, 3, 4. 1, 2, 3, 4. Okay, one more level. Okay. Okay. Pin 1 is over here, and pin 2 is over there. So if S is high, 1, 2 is through, and 3 is isolated. Okay, and then you have a ground, which I'm going to put here itself. And then I need S and S bar. So S I will keep at the top. So this is S. Come on. This is S, and this is S bar. And this is my switch. And I'm going to test this switch. So I'm going to do a test SPDT. Test SPDT. Create schematic. And then I'm just going to call in this switch here like this. And I'm going to put 3 terminals here. Simulation S parameter. Okay. 1, 2, 3. Okay. And 1, 2, 3. And ground. Okay. And I'll just connect it. 1, 2, 3. And I am going to use 2 supplies here. Sources, frequency domain. Okay, one I'll be using 1.8 volts. Apply. Put it here. Other I'm going to do as 0 volts. Apply. Put it here. Now, let me tell you this. You can always connect. You can always refer this point as a ground, but then this will be GND exclamation or what you call ground bang. Okay, so that's a global ground node. So that's why I'm putting 0 and 1.8. So I will name this one. Okay, so I will name this node as 1, O, capital O. And this one I'm going to name as Z or 0. So if I want the top part to be through, this should be O and this should be Z. Done. So now I'm going to do the S parameter simulation. So I would first here put include file, and then I would put a simulation S parameter. And S parameter simulation here, my band of interest is 27.5 to 28.35. 28.35. And I'm going to take step of 10 megahertz. Say OK, and I'm going to hit simulate. Okay, then I'm going to look at S21. This is my through path. Okay, so I'm seeing 1.2 dB insertion loss. So let's look at S11, S22, and S33. Okay, so these are over here. So what if I introduced inductance to move up? Okay, I can introduce inductance to move up, and this insertion loss will go down. Okay, so in my switch, let's go inside. Okay, over here, there are 2 ways of doing this. One is I can increase this capacitance, which will have a little bit of control, not much. Okay, this won't have a lot of control. I can also introduce the inductance over here because I want to go up, right? So I can introduce the inductance over here, delete, and again, I'm going to repeat this over here and delete. Now let's see what happens. Okay, up and simulate. So now I am at 1.1. right? And S11, S22, and S33. Okay, so around -13 onwards. Okay, and what about isolation? That will be 3.2. 3.2 would be the isolation, which is around 21 dB. Okay, so now, okay, let's me look at my previous design as I did some little cheating here. Close workspace. This is what I looked at under SPDT. Let's look at common elements. So there'll be a switch here, SPDT switch. Let's see what I did over here. Don't worry about this. 120 picohenry. So I'm using 15 picohenry here. I'm using 120, 15, 2 capacitors here, 1 big capacitor here, 50 micron here, 30 micron here. Okay, understood. So let me go back. Okay, go down. Okay, so 100, 100. So basically you do some few iterations, 15, 15, right? And what else was there? This was 50. Okay, so it will be 10. And this was 30. So 630. Okay, same thing over here. This is going to be 10. And this is going to be 30. Okay, 30, 50, and 30. 50 and 30. 100, 100. Go up, simulate it once more. Okay, so now I am seeing an insertion of 1 dB. So I'm seeing an insertion of roughly 1 dB across. And the worst case return loss I'm seeing as 18. Worst case return loss is 18 and isolation is 23 and match is like this. So I've done a little cheating. Of course, you can also, work with this and see what you get. Anyways, so this is the switch I'm going to use. So now let's put together the 5-bit phase shifter. So new, okay, and I'm going to say TS 5-bit. So I'm going to stop in another 10 minutes. So bear with me. Okay, let me just put it together and we will stop. We will test it tomorrow maybe. Okay, so I want a switch here. Okay, SPDT switch here. So this is one. And then I need elements. I would need a 180 element. So that's a 180 element. Maybe I made this very big. Okay, so you can make it small, doesn't matter. So this I'm going to repeat and mirror this like this. Right, and this is your 180 element. So in this case, I'm going to connect high pass element this way, low pass element this way, and ground this way. Done. Okay, and escape. Okay, so now I'm going to repeat this. So I'm going to take this. So this is going to be 90. Then this is going to be 45. Then this is going to be 22.5. right? And then this is going to be 11.25 and done. Now all the grounds I'll connect. Okay, so this I will connect to this ground. Okay, so this and this ground are connected, and this is connected. So all the grounds are shorted out, right? So all these grounds I'm going to short out. Okay, so this is a common ground. So this is ground for everything. And I'm going to put a ground pin here. Okay, so this is the ground pin. So we have given ground to everything. Now this is 180. Okay, so the next one is 90. So just change this to 90. Okay, the next one is going to be 45. So this is 45. Okay, the next one is going to be 22.5. So it will be 22_5. Okay, so this is 22.5, and this one, the last one, is going to be 11.25. Sorry, _25. Okay, so we are done. We have got 180, 90, 45, 22.5, 11.25. We have got the ground. We will have one P in. Okay, so this is my P in. And then we will have P out. And this is going to be symmetric. So input output terminal doesn't make any difference. Okay, you can put here your P out. So that's P out. Now what about the pins? Okay, so S0, S1, S2 and onwards, right? So you have S0, which is the LSB. Okay, so this is going to be S0. So this is S0. Next, this is going to be S1. Next, this is going to be S2. Next, it is going to be S3. And next, it is going to be S4. And then SB0. SB0. So this is going to be SB0. This is going to be SB1. This is going to be SB2. This is going to be, oh, did I do a mistake here? It's okay, it doesn't matter which one you are on. No, I'm okay. Okay, so this is SB3 and this one is SB4. Now, what about these? These will be shorted, right? So this is one pin. So this is one. This is the second one. Okay, this is the third one. This is the fourth one. And this is the fifth one. Done. So we are done with the 5-bit phase shifter design. And I'm going to make a symbol for this very quickly, and then we will test this tomorrow. So let's make a symbol for this. So 5-bit shifter, and I would do a new symbol, say okay. And in this case, I'm not going to do anything, just rotate this guy. Okay, so I have ground terminal here, P in. I'll pick up P in and put P in over here, and P out I'll pick up and put the P out over there. Okay, and this ground I can rotate and put it like this, ground over here. And then you have got S0 to S4, which I am going to mirror it out. S0 to S4, LSB to MSB like this. And this one is also I'm going to mirror out. Okay, done. So now you have got, for distinction, let's put it here. Okay, so you have a symbol for 5-bit phase shifter. Right, so we are done with the 5-bit phase shifter, and we are going to stop here for today. So today we did a LNA design, and we did phase shifter design. Tomorrow we'll do the attenuator design, and attenuator design is very simple. It's just that if you go to my presentation, you have certain formulas. Okay, so there is your formulas for T and pi elements. So this one is T pad, and this one is pi pad. And all you have to do is choose some for T and some for pi. For some, you are going to use pi, for some, you will do T. And how you're going to choose? You want to keep the component spread to be as small as you can. So either use T or pi, but make sure that the component spread, what is component spread? How much percentage is the lowest element of the largest element? So that's the spread. Okay, so I'm going from 0.5 to 16 dB. So this will be a 32 dB digital attenuator with 6 bits. Okay, and the switch element is going to be common, and then we construct these T elements, and then whatever is the delay on this, we are going to include a delay line on each pad. Okay, and we will put them together, and then you can have attenuation from some value, which is the loss of the switches, right? So which will be around 10 or 12, because each one has 1 dB. Per bit you have 2. So each bit is going to have 2 dB of loss. So 6 bits are going to have 12 dB of loss. So you will start from 12, and you will go 12 plus 32 is going to be 44. So you'll going up to 44. 12 to 44 you will go. And then the return losses will match, and the phase errors are going to be within 0.1 or 0.2 degrees, plus minus 0.3 degrees maybe, and that would be your attenuator 6-bit. You can test it. It's the same construction. Similarly, over here you have this construction, which is same, and then these are the phase going from 0 to 348 point. Sorry, this is going to be 348 point something. From 0.75, 348.75, and then these are your return loss S11, S22, S33. Sorry, S11, S22. This is the LSB which is doing this, right? And then you are going to look at S11, S22. These are return losses. S21 is the insertion. So basically, on this you are going to see 5 bits. So 5 into 2 is 10. So you will see a 10 dB attenuation over here on the phase shifter. And then all you do is you are going to compensate that with a gain stage. Okay, you're going to compensate each one with a gain stage here. So the net effect on the gain is 0. And then this is your LNA, this is your phase shifter, this is your attenuator. So tomorrow we will try to complete this as fast as we can. And then we will go to mixer design and all that stuff. So tomorrow we have a very large thing to cover, and we don't have sufficient time because this is a lot of concepts and designs. Okay, so I will try to do the best I can. But if you are left out, like we are not able to finish it, you have this presentation as a reference. You have the PDK. So you use that PDK to construct whatever I constructed. So for example, this VCO I constructed. So this is your VCO, right? And you put the VCO, the mixers and everything, then the VCO you interface like this, and then you generate the quadrature. Okay, the way to download this is you click on, you don't do this on, well, you do this on mobile phone, let's say. You click on that's presentation which I have in LinkedIn. And when it opens in the full screen mode, on the right top, you will see a download button. So you'll be able to download it. Okay, so that's there. Just try it, you will be able to download. So I'm going to stop here for today. I'm going to pause the